Let's take a look at the simple machines known as the pulleys. As a review, mechanical advantage is the number of times a machine multiplies your effort force. 1 is the magic number that we focus on. If a mechanical advantage is greater than 1, that means it actually multiplied your effort force. So your effort force is low compared to the resistance that you're able to lift. As a trade-off, though, the effort distance is going to be higher. If your mechanical advantage is less than 1, that means the machine did not actually multiply your effort force. It was actually a little bit harder to do the work. Your effort force is high, but your effort distance is low. As a reminder though, mechanical advantage can never be less than or equal to 0. Your ideal mechanical advantage is your theory-based calculation based solely on how something is built, and it utilizes the distances involved. dE is the distance that the effort travels. dr is the distance traveled by your resistance force. Once you know your ideal mechanical advantage, you can use it to find your ideal effort force needed to lift a particular load. Simply plug in the amount of load that you're trying to lift, use your ideal mechanical advantage, and doing a little bit of algebra, you'll solve for the force of the effort. Again, what this gives you is ideally how much effort force you would need to put into a system to lift the desired load. An actual mechanical advantage is what you actually get when you go to use the simple machine. It takes into consideration things such as friction. To find your actual mechanical advantage, plug in the load that you're trying to lift and plug in the amount of effort required to lift that load. A pulley is like a lever consisting of a wheel with a groove in its rim, which is used to change the direction and magnitude of a force exerted by a rope or a cable. The pulley's ideal mechanical advantage varies depending on what type of pulley you have. Let's take a look at the fixed pulley first. A fixed pulley is simply a first-class lever with an ideal mechanical advantage of 1. It's considered a first-class lever because the fulcrum is in the middle, the load is on one side, the effort is on the other. The fixed pulley simply changes the direction of the force. That's why it's considered to have a mechanical advantage equal to 1. The amount of effort you put in is equal to the amount of load you are trying to lift. That cable being draped over the pulley is simply changing the direction of the force. A movable pulley, on the other hand, is going to give you an ideal mechanical advantage greater than 1. Okay, it's a second-class lever, and this has an ideal mechanical advantage of 2. It's a second-class lever because your fulcrum's on one side, your load's in the middle, your effort's on the edge. The force directions stay constant. So here, since we basically have 2 cables, each cable is supporting half of that weight, so your effort force is less than your load. Typically what we get is a combination of pulleys, so fixed and movable pulleys working in combination with each other. This is what's known as a block and tackle. The block and tackle provides a mechanical advantage and also changes the direction of the effort force. If a single rope or cable is threaded multiple times through the system of pulleys, your ideal mechanical advantage is simply found by counting the number of strands opposing the force of the load in movable pulleys. So if we look at the pulley system on the right, we have a mechanical advantage of 4. So there's 4 strings, 1, 2, 3, 4, that are actually supporting the load. This last one, highlighted in black, is only changing the direction of the force. Here's what that means. If I'm trying to lift an 800-pound motorcycle, if I have an ideal mechanical advantage of 4, it only takes me 200 pounds of effort force to do that. The actual mechanical advantage, though, remember, is just the force of the load over the force of the actual effort required. So the actual mechanical advantage of the pulley system on the right, we're able to lift that 800-pound load, but instead of it taking 200 pounds of effort, it took 230 pounds. 800 divided by 230 gives us an actual mechanical advantage of 3.48. The efficiency of this pulley system is found by taking your actual mechanical advantage divided by your ideal mechanical advantage times 100 So in this case, we're getting an 87% efficient system. More often than not, our simple machines are working together as a system. If one simple machine is used after another, the mechanical advantages multiply. Your ideal mechanical advantage total, in this example given, is the ideal mechanical advantage of your pulley times the ideal mechanical advantage of the lever. So we could find the ideal mechanical advantages of each one. So the pulley is simply our number of strands. The lever is simply the distance of the effort over the distance of the load. We have 2 strands. Distance of my effort is 12 feet on the lever. The distance of the load is 4 feet on my lever. So I would get a mechanical advantage of 6. This idea of a compound machine can be applied when we have pulleys in combination with each other. When I have separate ropes or cables, the output of one pulley system can become the input of another pulley system. This is considered a compound machine. So if we take a look at the ideal mechanical advantage of the pulley system on the left, start where we've got the load. And so we're just going to multiply the ideal mechanical advantage of each of these systems. This one has an ideal mechanical advantage of 2 because it has 2 strings. So each string would be supporting 40 pounds of force. Moving up, this also has a mechanical advantage of 2. 2 strings. The load that this one is lifting is 40 pounds, gets split in half. Moving up, we also have an ideal mechanical advantage of 2 because of the 2 strings. So we're taking that 20 pounds of force that it's supporting, cutting it in 2. So I have an ideal mechanical advantage of 8, which as you can see as we walked through it, I only need 10 pounds of effort force to lift 80 pounds of resistance force. One thing to be aware of is sometimes people say that angles and pulleys don't matter. That's wrong. Typically, a pulley's ideal mechanical advantage is the number of strands opposing the load, but that's only if the strands are opposite or parallel to the resistance force. So in the example on the left, those ropes are being supported straight up. If I have any kind of an angle in there, we actually have to use trigonometry to figure that out. So my suggestion to you is to always build your simple machines if your ropes are straight up and down. We'll eventually get to the trigonometry, just not this early in the year. If you have any questions about pulleys, please make sure you're asking me in class.